Okay, let's get started. So before I get into logic, a few announcements. The exam is tomorrow. Remember that. Next week is Thanksgiving break, so we won't have any classes. There's no more sections. And after you guys come back from Thanksgiving break, on the Monday, there's going to be a poster session from 2:30 to 5:30. So there's more details on the website, and we'll post more details on Piazza as well. And then finally, the day after, there is a logic homework due. So that's pretty much it, aside from the final report of things that you should keep track of in this class. I want to take a few minutes to talk about CoderLab worksheets. So this is a platform that we've been developing in our group to help people do research in a more efficient and reproducible way. And the thing that's relevant for 221 is that you will get an opportunity to get extra credit by using CoderLab worksheets, and also it provides additional compute if you're running low on that as well. I want to give a quick demo to give you an idea of how this works. So if you go over to worksheets.coder.org, you can register for an account. I'm going to demo a kind of a newer interface that you're actually going to see on the website, just because that's what's going to be rolled out soon. So let's create a worksheet, CS221 demo. A worksheet is like a Jupyter notebook, if you are familiar with that. And you can do things like write text. So I'm going to run some sentiment classification. And let me try to at least spell this correctly. So let's suppose the title is C21 Final Project. Okay, and then you can upload code or data. So I'm going to go ahead and upload the sentiment data set. Hopefully this sounds familiar to some of you. And then I'm also going to upload this text class.py, which is a source code. So each of these resources, data or code, is called a bundle in CoderLab, and you can look at the contents of this bundle, you can download it, and so on. It has a unique ID which specifies forever the precise version of this asset. And now the interesting thing you can do with this right now is you can run commands. So CoderLab is pretty flexible. You can run basically any command you want. You specify the dependencies that this command will need to rely on. And then you can type in whatever text class.py, train polarity.train test polarity.test. And then you hit confirm. You can also see over here, you can specify how much resources you want, whether you want GPUs, where you need to access the network, and so on. So this goes and creates a Docker image that's actually running, or Docker container that's actually running this command, and you can visualize the standard output in kind of real time as the command is running. And you can see the files that are generated. So for example, one of these files is just a JSON file that has the test error in it. So suppose you wanted to visualize your experiments a little bit better, because this is kind of just the default information, how big the bundle is, and so on. You can this is a little bit more advanced, but I want to show you how this works. You can define custom schemas. So if you define a schema which is called run, you add just some fields. You can actually specify test error as a custom field, and you say go to stats.json, read it out, and then now you use that table to the schema to define this table. You can see this is the test error. Let me make this a little bit nicer and format it to 3 decimal places. Okay, and then you can go and you can modify this command, and you say rerun. Maybe I want to try some other parameters. This eta is the step size. Let's try some more. You can rerun this 0.2 and so on. So you can fire a bunch of jobs, and you can kind of monitor them. So this one's running, this one's created, and you can monitor kind of various statistics that you want. So this is generally a good way to just launch jobs and kind of forget about it and keep track of all these things. So then you can say larger step sizes are hurt accuracy or something. So the idea behind a worksheet like in Jupyter is that you document your experiments as you go along. And so every asset, data, code, and bundles, and the experiments are all kind of treated the same way so that you can go in here and 6 months later and you know exactly what command you ran to get this result and the exact dependencies, so there's kind of no question. So you should think about this as kind of a Git for experiments. And if you go to the main side, you can actually fire some jobs with GPUs on them. Depending on how many people are using it, there might be a queue or might not. So if you want some extra compute, that's a good way to go as well. Question? How much memory can you typically get? So there's so one thing that if you want to find out, so it varies depending on what kind of resources are available. But if you type any sort of command like free, you can actually see the exact environment that your job is running. So I think you can get like maybe, let's say 10, 16 gigs of memory. Yeah. Any other questions about this? So there's documentation here, and if there's any issues that you run into, file a GitHub request or email me or something. Piazza won't have the highest you can post on Piazza too, but it'll be probably faster if you submit a GitHub issue, because I'll go directly to the team that's working on this. Yeah?
Does this only work with Python?
Does this work only with Python? You can run any command you want. So you can C++, Java. It's
install like Julia or something.
Yeah, you can run it on Julia. So the thing, when you do a run, you specify the Docker image, which is basically contains your environment. So if you have Julia, probably has Docker images available. We have a default one that has. I'm not sure if it has Julia, but it has kind of the standard Python, TensorFlow, PyTorch kind of libraries. Yeah.
So if you want to install some dependencies like PyTorch or Keyless, so that can also be done.
Yeah. So if you want to install some dependencies, there's two things you can do. You can build your own Docker image, which takes a little bit of work, but it's not too hard. Or you can, if you want to be lazy, you can just do pip install here in the command. And for that, you have to make sure you turn on network access so it can actually download from PyPy.
So we can have some requirements file and then run that.
Yeah. Yeah, you can have the requirements file. Yeah.
So does this support pop-up windows? For example, if you want to plot something during the middle of the run.
Does this support pop-up windows? No, this is more like a batch run. So the way there's several ways you can do this. You can actually expose like a port, so you can connect. If you're using TensorBoard or something, you can actually connect to your job on the fly. Or you can actually, there's a way to mount the contents of your bundle while it's running to local disk, and you can run whatever scripts you want. But maybe I'll hold off further questions. You come talk to me afterwards if you're interested and want to know more. Okay, just wanted to make that clear that thing is available. Go check it out. Okay, so back to the topic that we've been discussing. So on last Wednesday, we introduced logic. And remember, there's three ingredients of a logic. There's the syntax, which defines a set of valid formulas. For example, in propositional logic, it's rain and wet is a particular formula. So formulas are just symbols. They have no intrinsic meaning to themselves. The way you define meaning is by specifying the semantics. So we talked about the interpretation function, which takes a formula and a model which represents the state of the world and returns either true or false. And the way you should think more generally about a formula is that it carves out a set of models which are configurations of the world where the formula is true. So in this case, there are 4 possible models, and rain and wet corresponds to this set of models, which are in red here, where it's raining and wet. And finally, we talked about inference rules, where if you have a knowledge base, which is a set of formulas, what new formulas can be derived? So one important thing to remember is that these formulas are not meant to kind of replace the knowledge base. These are things which are derived, which could be very simple things as you have a lot of knowledge about the world, but you might want on any given context, you might know that it's raining, so F is generally much smaller than the knowledge base in terms of complexity. So for rain and wet, you can derive rain. Okay, so in general, we run inference. What does it mean to do logical inference? You have a knowledge base, and then you have a set of inference rules that you keep on churning and churning, and then you see if you produce F. So an example we saw last time was modus ponens, which says if you have wet and weekday implies traffic, then you can derive traffic. So the things on the top are called premises, and the things on the bottom are called is the conclusion. And more generally, you have this modus ponens inference rule. So now the question is, what does this inference rule have to do with semantics? Because this is just symbol manipulation. You saw these symbols, you produce some other symbols. And in order to anchor this in semantics, we talked about soundness and completeness. So entailment is a property between a relationship between a knowledge base and a formula which is given by the models, right? So the models of F have to be a superset of models of KB. That's the definition of entailment. And separately, we have the notion of derivation, which is symbol manipulation. You can derive F given a set of inference rules from KB. And soundness means that the set of formulas that you derive are always entailed. And completeness means that you can derive all the entailed formulas. So remember this water glass analogy, where this set of things in the glass are true entailed formulas, and you want to stay within the glass, but you don't want to spill over. So far we've looked at propositional logic, which is any legal combination of symbols, propositional symbols, and their connectives. We also looked at a subset of that called propositional logic with horn clauses, where all the formulas look like this. You have and of a bunch of propositional symbols implies some other propositional symbol. And so there's a trade-off here. So we saw that propositional logic is not, if you use modus ponens in propositional logic, you're going to be sound, but you're not going to be complete. There are certain types of formulas which you won't be able to derive. So we could either restrict propositional logic to only horn clauses, and we showed last time that this indeed is complete. Or we can say we really want propositional logic, the full expressive power, and instead we're going to do this thing called resolution, which we're going to talk about in this lecture. Okay, so this lecture has 2 parts. We're going to talk about resolution for propositional logic and then move on to first-order logic. Yeah?
Just going back to the last slide, when it says that conversion with horn clauses is complete, does it mean that anything we could represent with propositional logic and resolution, we can still represent with horn clauses?
So you're asking about this last statement, or?
The last 2 together, are they effectively equivalent? Is anything I could do with the last one something I could do in the second to last one?
So the question is anything I can do with the last one, anything I can do with the previous second to last one? So it depends on what you mean by do. So these are different statements about expressive power and inference rules. Propositional logic subsumes propositional logic with only horn clauses. So you could just say, I only care about propositional logic. But it turns out this is going to be exponential time, and this is going to be linear time. So there's a trade-off there. Yeah?
I guess what I'm trying to complete? Are we like saying Turing complete, or what kind of level of completeness are we?
So what is completeness? I'm using a very precise way to talk about of a completeness of a logical system. A set of inference rules means that anything that is entailed by the semantics of propositional logic is derivable via a set of rules. And a particular set of rules here is modus ponens for this case, and then resolution for this case. Yeah. So the completeness is really a property of resolution, the inference rule with respect to a particular logic. Yeah. Any other questions? Okay, so let's dive into resolution now. So let's revisit horn clauses and try to grow them a little bit. To do that, we're going to take this example horn clause, A implies C, and we're going to write it with disjunction for reasons that will become clear in a second. I'm going to write some of these identities on the board. So these are things which are hopefully you know. I also wrote this last time. This is just just true, I guess. This is I want to say definition, but it's not really the definition because the definition is the interpretation function. But you can check the 2x2 truth table, and this is true. Intuitively, P implies Q really just is the same as saying either P is false or Q is true. If P is false, then the hypothesis is false, so it's irrelevant what Q is. And if Q is true, then the whole statement is true. Okay. So what about this? A and B implies C. So I can write it as not A or not B or C. So this invokes another identity. So which is that if I have not of P and Q, that's the same as not P or not Q. Okay, so, and there's also another version, which is P or Q negated is the same as P, not P and not Q. So what I'm doing intuitively is pushing this negation past the connective into the propositional symbols. And when I push it past negation past and, it flips to an or, and when I push it past an or, it flips to an and. Okay? And hopefully you guys should be comfortable with this, because when you're doing programming and you're writing if statements, you should know about that. Yeah?
So if the parsing here is left to right, like is it A and B implies C, or is it like A and B implies C?
Yeah, it's a good question. So what is the order of operations? It's A and B parentheses implies C. Yeah. Okay, so if you apply the second identity on the board here, you have A and B is not A or not B. And then you apply the first identity, and that thing or C is the same thing over here. Okay, so now I'm going to introduce some terminology. First is a literal. So this is going to be either a propositional symbol or its negation. There's a notion of a clause, which is just a disjunction of literals. So disjunction means or. So these things are all clauses. And finally, there is a particular type of clause called a horn clause, which I introduced last time, but here I'm defining it in kind of a different light here, which is clauses that have at most one positive literal. Okay, so in these clauses, there is indeed only one positive literal, so these are horn clauses. If you remember from last time, if you have snow or traffic appearing on the right-hand side, then that has two positive literals, which means it's not a horn clause. So now I can write modus ponens the following way. So A and A implies C, which can be written as a disjunction, allows me to derive C. And here is another intuition, which is that I'm kind of effectively canceling out A and not A, and I'm taking the resulting things and putting them on the bottom. Okay. All right, so now let's introduce the resolution rule. So general clauses could have any number of literals. So this is not a horn clause, but it is a clause. And the resolution rule for this particular example looks like this. So rain or snow, and if you have not snow or traffic, allows you to derive rain or traffic. Okay? So this is not a horn clause, right? Because I have two positive literals. And how do we intuitively understand what's going on? So you could say, okay, it's either raining or snowing, and snow implies traffic, which means that if it's snowing, then I can get traffic. But if it's not snowing, I still have rain here, so I can conclude it's either raining or trafficking. So in general, the resolution rule looks like this. So you have a clause up here with some P, propositional symbol, and then you have a second clause with not P. And what you can do is you can cancel out P and not P, and then you can take everything else and then hook them up as a big clause. Okay. So this is a rule. I kind of sketchily argue that it's a reasonable thing to do. But to really formally verify that, you have to check the soundness. And the way you do soundness, remember, how do you check soundness? You go back to the semantics of propositional logic, and you verify that that's consistent with what resolution is trying to do. So in this rule, you have rain or snow. The set of models of rain or snow is everything that's not white here. The set of models of not snow or traffic is everything that's not white over here. And when you intersect them, you get the dark red. And that represents your where you think the state of the world is if you only have the premises. And if you look at the models of the conclusion, rain or traffic, it's this green area. And you just have to check that what you derived is a superset of what you know. And again, this might be a little bit counterintuitive, but you should think about knowledge as restriction. Knowledge means that you actually have pinpointed the state of the world to be smaller. So the fewer colored boxes you have, the more knowledge you have. Okay, so this is sound. Completeness is another much harder thing to check. Yeah, question?
So you mentioned that we wanted to have a superset at the end, not a subset, but there's the two topmost row tiles for snow alone or snow removed that are not there. Is that because we've eliminated snow?
This is, so why are these there? This square is only true in rain or snow. This is only true in not snow or traffic. But remember, the way to think about a knowledge base is the semantics is the intersection of all the models of all the formulas. So when I've intersected the models of everything up here, I'm only left with the dark red.
There's just one square in our final in the green cell that's not a part of the intersection. I'm sure.
There's two. These two.
Yes.
Yeah.
And we allow for those because of the fact that our conclusion is rain or traffic. But I'm just sort of wondering, when you're mentioning the superset versus subset, why then the other two squares up on the first row weren't included?
So let's see. Why are the ones up here not included? Because they're not part of the intersection. So is your question, why are these squares not part of the intersection?
But still included.
So they're not, let me clarify. So if you only look at the premises up here, the set of models is this square, this square, this square, and this square. Then you look at the premises, the conclusion, and you look at the models independently of the premises, and you get these 6 squares.
I see. So those 6 squares are not related to the 2 that we had beforehand.
Yeah, so this is, the green is just derived from the green here.
Got it. Okay.
Yeah.
That helps.
Okay, good. All right, so it turns out that resolution is also complete, and this is, kind of the big result from the 60s that demonstrated that even a kind of a single rule can kind of rule all of propositional logic. But you might say, wait a minute. There's clearly things that this resolution rule doesn't work on because it only works on clauses. So what if you have formulas that aren't clauses at all? So there's a kind of this trick that we're going to do is that we're going to reduce all formulas to clauses. Okay? So another definition that is important here is CNF. So it stands for conjunctive normal form. So a CNF formula is just a conjunction of clauses. Okay? So here's an example of CNF formula. Here's a clause, and you can join them. So it's important to remember that. So just to refresh, this is a CNF formula. It's a conjunction of clauses. Each clause is a disjunction of literals, and each literal is either a propositional symbol or its negation. Okay, so or is on the inside, and is on the outside. And the one way to kind of make sure you remember that is a knowledge base, remember, is a set of formulas, but really it represents the conjunction of all those formulas because you know all the facts in your knowledge base. And so you can think about a CNF formula is just a knowledge base where each formula is a clause. Okay, so we can actually take any formula in propositional logic and we can convert it into equivalent CNF formula, which I'll show in the next slide. And once we've done that, then we can use resolution, and life is good. Okay, so the conversion is going to be just a 6-step procedure. It's a little bit grungy, but I just want to kind of highlight the general intuition. So we have this formula. So this is not a CNF formula, but we're going to make it one. Okay, so the first thing we want to do is we want to remove all the symbols that aren't ands or ors or negation, because those definitely don't show up in a clause or CNF formula. So we can use the first identity on the board to convert implication into a not and an or. You do that for the inner guy here. And now you only have symbols that you're supposed to have. The second thing is that remember the order in which these connectives is important for CNF. So negation is on the very inside. Negation is only allowed to touch a propositional symbol. Then you have or, disjunction, and then you have and. So we want to change the order so that that is true. So first we want to push the negation all the way inside. And this is using the De Morgan's law. So the second and third identities on the board. So we push this inside so that now all the negation is on the inside. We can remove double negation. You can check, very easy to check that that's valid. And finally, so this is not a CNF formula. It might look like one, but it's not. If you turn your head upside down, it actually looks like a CNF formula. But the reason is that and is on the inside, but it really should be on the outside. And to fix that, you can actually distribute or over and, which allows you to say this is summer or bizarre and not snow or bizarre. Okay, so now this is a CNF formula, and then you're done. This is a general set of rules. Just to recap, you eliminate bidirectional implication to get the symbol inventory right. And then you move negation all the way to the inside. And you eliminate any spurious negation that you don't need. And then you move any or from the outside to inside the and. Okay? So, long story short, take any propositional logical formula, you can make it a CNF formula. So without loss of generality, we're just going to assume we have CNF formulas. Okay. Another place that you might have seen CNF formulas come up is when you're talking about, in theoretical computer science, when you're talking about 3-SAT. 3-SAT is a problem where you're given a CNF formula where every clause has 3 symbols and 3 literals, and you're trying to determine if it's satisfiable, and we know that to be a very hard problem. Okay, so now let's talk about the resolution algorithm. Remember, there is a relationship between entailment and contradiction. So knowledge base entails F is the same as saying knowledge base is incompatible with not F. Like F really, really must hold. It's impossible that not F holds. Okay. So suppose we wanted to prove that F is derived from the knowledge base. What we're going to do is this proof by contradiction strategy, where we're going to say insert not F into the knowledge base and see if we can derive a contradiction. Okay, so you add not F into the knowledge base, convert all the formulas into CNF